However, the very first initializations of the NPI happen at the very first step which the code runs. So it actually hasn't even read anything, including the IP name. So it actually doesn't even know what IP is, and therefore would never executed this in the past. So now it must either be always on or always be off. So at the moment it's on to make sure you can read what actually are the names of the sequences.
Don't we have stuff in the messages module for that?
You just simply don't know the value of IP.
It hasn't really any done.
Yes. So IP is just
I'm
always
something for being maybe. No, I think that's just the stopping the code.
Yeah, that's if one processor has a fatal error, if that's what you're thinking about, but if the others don't know about it, want to continue, then I think it's the degradation here.
So in the past there was a condition that, or there was never any question of whether possibly the processor number in the X direction is more than one. Now it can actually be. So therefore this is an entirely new piece in the code. So what is, and there are of course two similar pieces for the corresponding production of data to be transmitted in the Y and the Z directions. So what is happening here? This is the first piece where we are doing both the receive and the sending. Where of course each processor must send and receive, but of course from somebody else. So you should really think of this, of an MPI code, as not of an MPI code which handles this whole business really. But an MPI code is really something which is able to just run on this box. That's all you have really. You have a mesh of this size that is defined, and you have certain boundary conditions, and boundary conditions are being handled through buffer zones. So you must make sure that these boundary layers are being filled with correspondingly the correct data. So either you have a physical boundary condition, in which case you would know which values to put it. If it's a periodic boundary condition from over this domain, of course, these values would be equal to those values inside the domain of the other side. You would put those into the boundary layer. In an MPI code, of course, those points in the buffer zone have to come from this processor. So therefore, at this point, you will say that I want to receive from processor number 17 here. So I want to receive this. And if I got it, and I haven't got it yet at the first instance, I'm expecting to get data from this processor. I'm also sending data. And what I'm sending is, of course, not from this layer, but from the layer inside. That's what I'm going to send. I'm sending out data from here, and I'm sending those to the ghost zone of the other processor. So what I'm producing, first of all, is the stuff that I want to send. The stuff that I want to send is in my full F array, as it is like here. That's my full F array. F means all the vectors, all the variables on the state vector within certain boundaries. It may not be actually the full F array, because the full F array can contain diagnostic quantities that we don't want to communicate. So that's an additional possibility of the code.
It also goes the other way around. Sometimes you don't want to communicate everything, but you just for the shop, for example, you just want to communicate velocity again. That's why you can put I bar 1 and I bar 2, so that you don't share everything.
Yes. Right. Okay, so what we want to send, of course, in the X direction is only information inside the processors. So now you need to know the convention of the labels here. So this point is called L1. This point is called L2. This point is 1. And this point has the label MX. In each processor, that is. Now this point, which is also 3 mesh points inwards, has the name. Do we actually have the name?
L1I.
Huh?
Yes.
No, L1I, I think is. That must be right, yeah? Right. The L1I,
L1I.
L1I, yes. And then this one, of course, is L2I. Correct? Okay, so what I'm then sending, I'm packaging up everything into a packet here for the full array, that is. So I'm not communicating separately for density or for temperature or something. Everything is being handled in one go, and that's also simple. So therefore, if you're implementing a new variable, if you're introducing plus a scalar or something, or a neutral density or something, all the MPI stuff is also already taken care of by these steps here, of course. You don't need to worry about that anymore. So you're packaging up everything between the first mesh point, which is already inside the domain, and the next 2 points. So that corresponds, this will of course will be the value 4 for our scheme, and then 4, 5, 6, this will be the value equal to 6. So that's being packaged up into these kind of buffers. And that carries the name L for lower and U for upper, and buff for buff, or buff for buffer, and X for X, and O for output. So that goes out of this processor. And then it's supposed to be sent. So, and here are then the MPI library commands. So there are MPI receive commands. These are not the ones we need at the minute, but then there are the MPI send commands, and these are the ones where we stick these two prepared buffers into that. So they are this one here, lbuff XO, this one, and then this one here. The other thing that we need, of course, is names for the addresses. We need to send it all to the correct receiver, and these have names. So we have to send this one to the X lower neighbor, and this one to the X upper neighbor. Up and low refers to up and low in terms of the indices of numbers, not in the vertical Z direction, but it's any direction in space. So this one is always up, and this one is always low. So these are the two labels. To low X and to up X are the names to which it should be sent to. They must be unique, and so they are in fact defined at the very beginning of this whole thing. I think that you should have seen up here. I'm actually surprised I didn't see that here. It's certainly in the code. And we actually, let's just have a look here in the actual code. So here's, oh, now I know what it is, sorry. It's actually not in here, but it's to make it completely clear that everybody has the same data here. It's actually in C data. That's where it is. So, and where is that in here? Let's just look for this, of course. X low. No. Here we go. No, it's not. There's something with 13 in it at least. No?
It's the neighbor divided neighbor.
It's going to be defined. I know the numbers are 13 and 14 or something. Anyway, doesn't matter maybe. I don't find that. Oh, we can of course still look at for the. Let's have a look here. Wrap this with the equator. By the way, here we see that. So it was actually somewhere defined in here. It was for, and this grabber, if you find it, of course, but by searching, I didn't find it, at least not in this case here. So the numbers were 13 and 14, so they are unique and they don't come again. They're not being used by any other labels here. So, okay, so that is then being sent in the X direction. At the same time, we say that we receive stuff from a corresponding from the same processor to which we actually send. So we are just telling it that we are expecting new stuff to come in, and this will come into an array which has its name. Now we are principally making use of buffered I/O. That means that at the minute we are invoking this command, we are not expecting that this data exists actually. It exists only after we have asked it to have arrived. So in principle, we can receive data. We can say that we are receiving. That means please send us something within the next 10 seconds or something. But it will be free to do other things in the meantime before we expect that really to have arrived. But even though that is actually part of the MPI implementation in general, or MPI language, it's not actually part of the implementation on LAN MPI. That's correct, I think. At least not on Linux clusters. Okay, so here then we have the.
Axel?
Yeah.
Doesn't that maybe depend on which network? You know, whether they use InfiniBand, doesn't it? Or gigabit, or whatever.
Yeah, you know that?
I don't know it, but
this I have not heard.
but could be, I guess.
The only thing where I think, actually I don't really know for sure of any machine where it really works. So for example, on an origin machine, it doesn't really matter because the memory is already distributed. And that maybe that works, but it's not even important there. So here's then the next part where we, the corresponding matching part where we have received the data. So here comes then the command where we say MPI wait. So as I told you that we claimed already that we are going to receive something, but we are not receiving it yet at the minute. But by this time, this stuff certainly should have then arrived. These are the corresponding commands. And so, given then that the stuff from this corresponding process has arrived, we can stuff in this material from the corresponding buffers into the corresponding slots within the F array. And so these are then obviously points in the ghost zones. So between 1 and L1 minus 1. Remember, L1 is the first point in the domain, L1 minus 1 is the first point outside the domain, in the buffer zone. So these three points in the buffer zone are these here, and the lower part. They, of course, carry them this label, and here for the corresponding for the upper part. Okay. This was actually also interesting here. Of course, if you look in the pencil code, there are corresponding pieces for the y and the z direction. And of course, already when we were coding this, we were wondering why don't we do the same thing also for the x direction. And we have realized that during the first, we do it step by step, of course. We started the whole code back in Potsdam by parallelizing only in the z direction, and thought we can get a long way with that, until we found the first machine which actually had a problem with that. It was the Cray machine with 256 processors. So you cannot possibly run a three-dimensional problem by parallelizing just in the z direction with 256 processors. Already if you have a mesh with 512 mesh points altogether, you would only have 2 mesh points within each layer, of course. So that's ridiculous, of course. So therefore, almost immediately we had to abandon this concept and had to parallelize also in the y direction. And we found that it took a long time still before we could debug everything. And of course, that is still going to haunt us, this debugging of the x direction. And it was a lot of trouble because it took at least until the summer of 2006 before finally the last pieces were hopefully removed, the 5 last bugs in MPI. You're looking, right? Oh, what do you mean, bugs in this? You of course came online after 2002, no?
And you said 2006?
No, 2.
Oh, 2.
So we started this in 2001 and debugged until 2002. These things were running already, of course, except that in certain cases there were problems with certain corners. So it was something which you may almost ignore, except in a few strange cases. And then there was therefore this comment, we may never want to do this after having seen all the trouble involved in parallelizing over 2 directions. So it must be much more of a nightmare parallelizing over 3 directions, of course. So obviously I've taken out this comment and then replaced it by this corresponding chunk first of all, ignoring that there may still of course be problems ahead. So these are all the differences here. Why is this actually different? Somebody else did something else here. Okay. Alright, so with all these preparations, I just want to show you that in principle that actually works. It works for 1, 2, and 3-dimensional problems. I tested this for so for two different 2-dimensional problems and one particular 3-dimensional problem. So let me then do the samples first of all. So we are having here the standard samples with helical MHD, for example. This may not be up to date here, of course. Why is that? Because of because I turned simply off the consistency check. Because that takes some time, and I changed number of time steps to this, which is not important. So I just remove this and I say CVS up again, of course, so I get the fresh file here. But what I wanted to do now is I do a new run. So you know that doing a new run is called PCU run. And you can do it in a new directory. So let me do it in a parent directory, and I want to remove it anyway afterwards. So you should not. So that is an NPI or parallel X, I call it. So then I go into this directory. So that was now the standard test here, of course. So what do I need to do in order to run? I, of course, go into the 2.local files as usual. In the first one, we will now have to do the following change. We say that we want to run on 8 processors. We have, we no longer have an NX of 1, but I want to say we have an NX of 2. So I put it here and say NX is equal to 2 and Y is equal to 2. And then obviously this must be, and proc Z must be equal to the total number of processors divided by the product of these two. So that means I have this. Yes?
I have a question. So when you define n plus, normally you must see the same number in the run command.
Yes.
That's right. Is it written by setup SRC or?
Yes. The MPI itself is writing out, when MPI starts, Fortran knows how many processors it actually has.
Yes, because
so it may be, first of all, you have to tell the queue already how much it is. And there's an automatic Perl script which Wolfgang has written, which reads from exactly this one how many CPUs it actually has.
No.
So you submit this to the queue, and then it reads from this file how many processors it actually has. And then you get onto the Fortran job. So suppose, for example, there's a mistake.
There is a mistake. Okay. No,
suppose there is a mistake.
Yes.
This can go onto a machine, into a queue which has, for example, 16 processors. That can happen.
Okay.
In principle. And then of course you run the MPI job. MPI knows exactly how many processors it should have, and it says it has 8, and then it will output 8. And it may or may not find this okay, of course.
Mm-hmm. Okay.
But these numbers are not normally different when everything is okay. There's certainly is a mistake in one of the something. It's the definition of some machine name even or something.
Okay.
Anyway, so this is the first thing. Here's the MPI, the make product local, and of course we have to go to MPI. So these are the two steps we have to do. Remove the no MPI.
Mm.
And then you compile the whole stuff, of course. And that takes some time. In the meantime, I can explain the business about these corners. So let's see how this works. So at the moment, we have just simply parallelized in the additional x direction. But let me explain first of all the business with corners in the y and z plane, the traditional thing. So what we have done is we are concerned about this layer here. this has been, this is the first gallstone that has been filled. Then this gallstone has been filled. Then this gallstone. And finally this gallstone. So there are 4 corners that are missing. And so these 4 corners were then replaced by 4 additional routine chords, of course, but 4 additional buffers for the corners. In the present implementation of this X direction, the situation was slightly different to start with. And I noticed that I'm not going completely parallel to how things are in the Y and Z direction at the minute. And I simply said I will take care of it later. So what do I mean by this? So we had this was here in the Y direction, and that's in the Z direction. Now I'm making a corresponding plot between Y direction and X direction. So here's the X direction and the Y direction, and of course in the Y direction is now this one here. I am having these arrays here. They were already defined. Now in the X direction, everything, by the way, the length from here to here, you know, is called nx. And the length from here to here, that's called mx. So this does include the 2 gallstones, this excludes the 2 gallstones. And it just happened to be like this, that all the buffer sizes were always defined with a length equal to mx as opposed to nx. Whereas the buffer sizes in the other 2 directions, in the Y and Z directions, always had the corresponding lengths of ny and nz. So here the length, of course, is ny, and this length here is nz. So that meant that in the first instance, when we are communicating data, we have an array which has a size here. That's how it's working at the moment. So that means, of course, that this stuff is being filled with the material that is in here. So the stuff from here is being put into here. And this material that is in here is being pulled into here. So that's how technically it is working at the moment, and that may not, is probably also not right really. But let's demonstrate first of all how the whole code actually runs. So that was the start. Here, by the way, you see then the neighbors, and I told you that. So, for example, this means that on processor number 2, unfortunately I erased these things now. On processor number 2, which means IPX is equal to 0, IPY is equal to 1, and IPZ is equal to 0 again. We have the following neighbors. What that means, these numbers, you have to look them, identify them, of course. This goes in the circular direction. There's 8 numbers, because there's 4 corners plus 8 sides. So they carry the processor numbers and 0, 4, 6, and so forth. And before I actually saw these numbers, they were actually first wrong. And when the numbers are wrong, you wouldn't even have finished the code. The code will still be running at this moment, because it's still awaiting data. So in this case, it has obviously succeeded. A very good sign. So now we can run, and let me, while I'm running here, let me call him X terminal, because, of course, many of you, why is it black here? I want to do the right terminal, of course, and I have to do my private command here, of course. So I'm doing a top command here, and then I'm running simply the code in this window below here. So you should all realize that on a laptop, of course, you can run MPI jobs, no problem with that. But of course, the amount of work it takes, the amount of time it takes, will be such that MPI said, okay, you have 8 machines, so let it all run. And unfortunately, the machines are all the same. That means each process is getting only 12% here or something like this. So now the MPI job is of course running on this poor little laptop here. Cannot actually really parallelize very efficiently. But at least I can check that everything is working otherwise technically okay. And I think this one is hopefully only just taking too long. Just here, by the way, you see that's how it was called, how the job was actually called. And so MPI run, this happens all automatically, of course. MPI run minus MP8 and in the actual script. Now, in this case, if it really is not running, then it may indeed mean that in this case it's not working. Although I think at least a week ago it was working. So that may mean that there's a new issue, of course. By the way, if you may often find that you develop something new, and all of a sudden it doesn't actually. So it continues to work, and then all of a sudden it doesn't work anymore. And so my suggestion then is to actually produce a corresponding entry in the order test. And such a thing I actually happen to have done here, in this case I believe. So that means you should have a corresponding, let me actually stop this here. I have some, I'm not sure this is working correctly here. So let me then go into this one here. So there is this PC pencil code runs directory, which many of you may have checked out because it also comes with a public release. And there's a directory for 2D tests. And then there's an Alvin wave number test, Alvin wave test, which is even 3-dimensional, and here's a 2-dimensional test. And this is a parallelization or layout in the XZ plane. No. And this one here. So if I'm lucky, there may be a reference file in here. Maybe there is not in here. Maybe it's in here then. Yes, so here you see there's a reference data file. So if we were to run this, we should produce data that are exactly equivalent to this. So let's, first of all, this is the compiled version here, I believe. Let's see how old that is. By the way, there's this command here, which of course, but you remember this? Build time here. So that way you see when it was actually built. It was built on the 11th at 10 o'clock in the morning. So, so let's just start this. That cannot take too long. That's just running for four processes here. Oh, maybe something is doing it. What's that? Done? Oh, I think what happens, by the way, that may actually really have happened in the other case as well, now that I think of this here. Because, of course, I have several windows open, the output may have been produced in another window. What about this possibility here? Yeah, that may be, I'm not sure whether that was the right one, of course. But it does not, under MPI, it does not come, it happens, it depends on who is the root processor, of course. Only the root processor is writing data, of course. So anyway, it has produced new data here. You can verify this by looking at the time of the data file. So data, and then time series of that. So this time is equal to now, 3:15. So soon time to copy. And now we can check the differences here between the data and the time series and the reference data, and they are the same. So that was a compiled version. But now I'm going to recompile, of course, the whole code. And if somebody changed the code, and if the test is sensitive enough, it may, of course, capture this as a difference. I mean, we have been doing some development, of course, over the last week, so things may have happened. They may also be detectable through this, and maybe and maybe something was broken in the meantime. So anyway, that's the status of the parallelization in the x direction. So the conceptually, at least, that's how it works, and I think this needs to be improved because obviously, if it does fetch data from this here, these are not normally yet the data at the current time. What would be the data at the previous time, for example? That's the reason why it hasn't turned out here at the moment. So I think we simply need to go through the code again, redo the corners separately. You can either include, of course, or exclude the corners in the first attempt, but you should also be able to exclude them, and then do the corners here. And that is, of course, just an additional piece of work. But the overall framework of the things are already in place here. And so I encourage people to try and look at this piece of the code and help developing this further.